All right, we are recording our last session in acoustics for the semester. Yay! You can say you're just about shed of this course, just about done. We're going to be covering three things regarding hearing aids in this course. You can see this ear mold of a hearing aid. And you'll see it's got two holes in it. One for the sound, one for the tube, and the other one is what we call a vent. It's got a hole in it, and I'll hold that more closely. You can see two tunnels going through it, okay? That's one thing we're going to cover. The next thing we're going to cover is the fact that some hearing aids have a little filter, that little red thing. You'll see that stuck inside the hearing aid. That's called a filter. And the third thing, and the last thing we'll cover, and no, ear molds don't look like this sponge, okay? But this is just to show you that tubing is very narrow. It's a small diameter, but it gets bigger going out. So it's like a horn. So vents, filters, horns. Those are the three things we're going to cover today. And of these three things, the most important is the vent. Now here in today's hearing aids, I'm holding up a Today hearing aid, and if you look very closely, you're going to see there's a tiny little behind the ear hearing aid, and the end of it is sticking inside of your ear, but look at all the holes there. Okay? That is called a dome. I'm holding up a dome here so you can see it even closer. And you see this weird little rubber thing. And that's what sits inside of a client's ear. So we are not always using ear molds. Okay, this is for more severe loss. This is for less severe loss. But look at all the vents in that. Okay, even more than that one hole that you saw. This is really what they call an open fit. So we'll be talking about those things in this particular last Zoom session. And it's kind of just a way to finish off acoustics. You've had all kinds of frequency, wavelength, speed of sound. We covered the decibel from hell. Then we covered complex sounds like speech. Then we had a midterm. And then we covered psychoacoustics, loudness, pitch, minimal audible field, minimal audible pressure, all that crap. Masking, you know, fawns and sones and mells and all kinds of weird stuff. Now we take it all home and regarding hearing aids. Now, hearing aids are all programmed on software. Okay, as you know, hearing aids today are all digital. They're programmed on software. So we're not talking about programming the hearing aids on software because that is something you will be learning in later courses. The purpose of this particular Zoom session is to highlight those three things I'm mentioning, which are non-electronic. They have nothing to do with electrical current, software, nada. They are non-electronic acoustic modifications in hearing aids. So let's go and share screen, and we'll pull up the notes here to look at and see what we've got. So when you're talking about these particular things, we'll read this first section here, and then I'll show you a PowerPoint slide that deals with it. These are a bit of a lost art. Most hearing aids today are digital, which allows for amazing amounts of frequency shaping. So we can shape the frequency response to do anything we want. Okay, you can even do this if you want. You can make the frequency response do anything you want with today's hearing aids. So if somebody has good hearing in the low frequencies, you can deliberately give high frequency. If somebody's hearing is good in the lows and goes down in the highs, you can deliberately give more treble and less lows. You can do whatever you want based on the client's audiogram. Hi, Nicole. Thanks for joining. Okay, you haven't missed much, so here we go. Actually, we're just about all done. No, I'm just teasing. Okay, share screen now. Back to our notes. But non-electronic acoustic modifications are techniques used when fitting quite inflexible analog hearing aids. You're not doing that anymore. They help shape frequency response. Any good HIS should have a handle on these. Besides, implementing them is cheap. Now, this stuff here is stuff you've all heard before. So I'll pull my cursor away and just read this with me. The resonance of your outer ear canal is like an open cylinder, right? Much like a cup. Closed at one end, open at the other. I'm not turning it sideways because this is full of coffee. So, but you know what I mean. Quarter wave resonators, right? Open canal, closed at the eardrum side, open at the other end. And your ear canal is 2.5 centimeters long, which is about 1 inch. It's going to resonate with sounds that are 4 times its length. Witness this, 4 times 2.5 centimeters equals 10. And we want to figure out what frequency that would be. Well, 10 centimeters is 1/10 of a meter, 0.1 meter that I'm highlighting right here. So if you want to figure out what the frequency is, we knew how to do that from acoustics. Frequency equals speed of sound over the wavelength. All right. Wavelength is speed of sound over frequency. Speed of sound is, frequency is speed of sound over wavelength. So we know the wavelength, okay? 0.1 meter equals the speed of sound over x, and we want to find x. So 1 times 340 is 340. 340 divided by 1 is 3,400 hertz. So the resonating frequency of our outer ear canal would be 3,400 hertz. But we know that the ear canal is made out of flesh and bone and cartilage. So we know that that resonance is spread out. And therefore, you know that the resonant frequencies of the outer ear canal basically stretch from about 1,500 to 4,000 hertz. So these exact frequencies are fudged a bit. You also remember that the peak ear canal resonance is 2,700 hertz in the average adult. Studied that in anatomy of the outer ear. So here's the thing. Hearing aids plug up the canal. They destroy that resonance because you are now taking the hearing aid and you are plugging up the ear canal. Look, now I've just drove a truck over my ear canal. I've closed it with an ear mold. I put a hearing aid in it. So now I've plugged the open cylinder. It's not going to work so good anymore. That is why, sharing screen again, go to our PowerPoint and look at here. Here's speech. Remember the spectrum of speech? Vowels, louder and lower, high frequency consonants, softer and higher frequency. This is when the decibels are going up, of course, remember. And on an audiogram, of course, it goes down because decibels are increasing when you go down. So the loudest parts of speech are lower, and these are the vowels, your Z, V, M's, anything that uses the voice. These are softer. And here's your ear canal resonance that we just talked about. The peak resonance at 2,700 hertz. Then it starts at 1,500. The peak is at 27. It starts to drop off past 4,000 hertz. Well, put the truck in and drive it in reverse and drive over top of this, because that's exactly what happens when you plug up an ear with a hearing aid. So this resonance is meant to lift these high frequency sounds, to make them more audible for us so we can hear them. Now, when you plug up an ear with a hearing aid, you've lost that love and feeling. So here's the picture. Here's an open ear canal. Here's your resonance, your open, unaided ear canal resonance. And to you and me, that sounds just like this. It sounds perfect. It just sounds normal. Now you're taking, look at the bottom. You're taking a hearing aid and you're plugging up the canal. So now, if the hearing aid is giving you this frequency response, you'd think that that would be happening. But when you put it in an ear, because you've driven a truck over this frequency response is really more going to be like this. Okay? You've lost some of that high frequency resonance. All of this is to tell you that hearing aids have to A, provide gain, and B, make up for some lost resonance there. Anyway, one thing to look at here too, I'll share it and we'll just go back a couple of slides here. Let's look at ear mold impressions. I'm going to take this hearing aid out of my ear and we're going to stop sharing for a second and I'm going to show you the ear mold close up again. Okay, you can see the tubing going in. You can see the vent, the hole below the tubing. When I turn it toward you, you can almost, the light isn't perfect here, but you'll see there's two holes, okay? You can see two tunnels. One is for the sound to go through the tube, and the other one is a vent to let the air communicate. What we have here is a failure to communicate. Okay, anyway, so now that ear mold is sitting on the end of a hearing aid. This is the BTE, behind the ear. It's important to remember that the tubing is called number 13. I didn't make it up. It's not number 14. It's not 12. It's called number 13 tubing. And when you look at the tubing close up, and you look at the diameter of the tubing, so I'm going to turn this toward you so you can see the diameter of the tubing. It ain't much. It's very, very, let's see if I can do that here. You're looking at the internal diameter of the tube. That is 2 millimeters. Now, what's a centimeter? Your fingernail. Okay? Divide that in 10 parts. So it's 2/10 of your fingernail. Okay? It's narrow. Now, these are used on high power behind the ear hearing aids. So this is a humdinger. This is a high power BTE, behind the ear hearing aid. This ear mold, you should write this down, is called a lucite because it's made of plexiglass. Lucite, L-U-C-I-T-E, lucite. Lucite, and it's a skeleton. That's the style. Lucite skeleton. It's got that hole. See that big? I can almost put my whole finger through the hole. I mean, it's got this great big, and that's just meant if I stick it in my ear, okay, you may be able to kind of see it. I don't know. It's kind of hard to tell, but you know, that hole is just there so it doesn't plug up the whole ear. It's just a style. That's all it is. Now, contrast that to this ear mold. This ear mold here is rubber. I can bend it. See that? It's made of silicone. This is hard as a rock. This is plexiglass. This is silicone. Now, silicone, notice that this ear mold here, this silicone ear mold, does not have a vent. There's no hole. The only hole is the hole for the sound to come out. Okay, the tubing goes into the ear mold, number 13 tubing with its 2 millimeter diameter, and it goes out the hole here, I should say, out the hole here into your ear canal. So these ear molds are called full concha because they fill the whole concha, so they're not skeleton, they're full concha. So the style is different. It's not skeleton, this is skeleton, and this is full concha. And the second thing that's different is this is made of lucite, plexiglass, and this one's made of silicone. Now, silicone really adheres to the skin. Silicone doesn't let any sound leak out. So this is for profound hearing loss. If you see someone walking with a white looking ear mold, and it fills the whole concha bowl, you know that guy's got a whopper of a hearing loss. You're going to have to stand in front of him, let him see your face, because he's going to be using his hearing aids and his hearing aids to hear what you're saying. You know what I'm saying? Okay. Lucite skeleton is kind of more for severe loss, not quite profound. Okay, severe being like an 80 decibel hearing loss. Profound is 90 plus. Okay, it takes 90 decibels or more to just barely hear a sound. Severe means about 80 decibels or more to just barely hear a sound. Okay, so you have your degrees of hearing loss, and you'll be learning this in audiometry. You're going to be in 130. You're going to be learning all about this stuff. So I'm just giving you a heads up here. Okay. Now today, what we have a lot of is this kind of a hearing aid. Now this kind of hearing aid, the tubing is really thin. It's not number 13 tubing. Okay, it's not. It's very thin, and if I put this, now you'll have this little white tip. That's what's fitting inside the ear, and that's just called a dome, just a little, because it's shaped just like a dome, okay? And then this weird string sticking out of the end, you may be wondering what the Sam Hill that is, okay? That's just to anchor it in my concha. So if I put this guy on, you will not even believe how invisible that is. So I'm putting this guy in, and I'm having that little string sit inside my concha bowl. And the only thing you are going to see is almost nothing. Okay? That's called a thin tube BTE, thin tube. And the tubing is not number 13. It's not this kind of tubing, okay? It's not 2 millimeters in diameter. It is 0.8, like less than 1. It's less than half the diameter of this tubing. Thin tube. So these have come back big time, okay? Behind the ear hearing aids are no longer these big beige bananas, okay? Behind the ear hearing aids now look a lot like that, okay? And they fit behind the ear. The tubing is smaller, okay? The diameter of the tubing is smaller. Now here's the last style. It looks just like the thin tube. Looks just like the thin tube, okay? It's same kind of thing, tip on the end, almost identical, except that this hearing aid, sound doesn't go through the tubing. Okay, sound doesn't. In this tubing, and it's hard to show, you can hardly see it from Canada here. You're selling them all over Joplin, Missouri, and San Antonio, Texas. This is the most popular hearing aid around. Hey, there you go, you got one. It's called a receiver in canal, RIC. There's a wire going through the tube. Okay, no longer like the thin tube where sound is going through the tube. There's a wire going through it, and the speaker of the hearing aid itself is in the end. Okay? Whereas in the thin tube hearing aid, the speaker is inside the hearing aid, and sound is coming out of the tube. With the receiver in canal, the mic is here, but the receiver is at the end, spitting into your ear. Okay? But it, too, has holes in the mold. Holes in it. Holes in my confidence, holes in the knees of my jeans, okay? Now, let's go and look at your notes and break down the three. I'm waving at my better half who's just leaving here. Okay, let's take a peek at some of the three main non-electronic acoustic modifications. Now, are any of you at OTC, are any of you taking ear mold impressions of the ear? Are you doing that yet? Here's a picture of how you're going to be doing it in your labs. You're going to jam a sponge down the guy's ear canal. Then you are going to be mixing material up, putting it in a big fat syringe, and you're going to fill up the ear with goop. Okay? And you're going to fill up the whole ear for 5 minutes, and you're going to let the goop harden. And then you're going to take it out of the ear, and you want to see the whole canal, the whole concha bowl. These are examples of poor ear molds. This is an example of a good one. Now, you are doing this only when you are making ear molds like this. Okay? Or if you're making swim plugs for someone who's got doesn't want water in his ears, or if you're making custom earplugs or something, then, or if you're making ear molds like this. If you are fitting hearing aids like this, ear mold impressions aren't important because these are stock. You pull them out of the drawer, you look in the guy's ear canal and stick it in his ear, okay? But I'm just giving you a bit of a contextual information as to when you take ear mold impressions. Just remember, you never get a second chance to take that first impression. Ha ha. All right. Now, over here, when you have a good impression here, you've got two bends in an ear canal. You have one bend here. Here's the concha bowl. You have one bend and a second bend. So ear canals are kind of like a dog leg. They're not like a straight cylinder. Okay, they have a bit of a dog leg to them. A good ear mold impression is long because the manufacturer can cut off what's not necessary. But it's better to give too much that they can remove rather than too little. You also take ear mold impressions when you are ordering custom hearing aids like this. This is an ITE, in the ear hearing aid. Ugly as the day is long, but I'll see if I can put there, puppy. It's not even made for me, but looks like someone took a wad of bubble gum and jammed it in my ear, okay? It's got a volume control battery on it, but one thing it's got too, if you look closely, there's the faceplate, the volume control, the battery door, and if you turn it around, you'll see the shell. Oh, look, there's two holes again. The white one is for the sound, and the other one is the vent. And the vent is the hole in the hearing aid. You'll notice at the bottom of the hearing aid, where is this puppy here? You'll know, yeah, right there at the bottom of the hearing aid. Where can I, there's the hole at the outside. And that hole just below the volume wheel, which is by my fingernail there, that's continuous with that hole. So most hearing aids have two entries. One for the sound, the other one is the vent, and it allows the air to communicate behind the ear, behind the hearing aid, and outside the hearing aid. So when you're ordering hearing aids like this, you also have to take an ear mold impression because they have to know the shape of the ear. And some hearing aids are called in the canal. They're smaller. It's even got a piece of fishing line so you can grab it and pull it out of the ear because it's so small. And if you're looking closely, okay, you'll see a battery door, kind of, sort of. Well, I can open up this there you go. I've opened up the battery door, close the battery door, and I'll turn it toward you again, and you will see two holes. One for the sound, one's the vent. And if I turn the hearing aid around, there's the vent on the outside. And that hole is continuous with that hole. Okay? Vents. Hearing aids can get really small, completely in canal. Okay? Tiny little, there's a vent on the outside. See the little hole? Okay? That's continuous with that hole. And again, there's two holes at the end of the hearing aid. The white one is the speaker, the receiver, and the other one's the vent. Just showing you. So that's a little more hands-on than the usual talks you're getting in acoustics, isn't it? Okay? I told you we'd end on a different note here. Anyway, there's two ear molds that I want you to look at, and it's the far left one. That's the full concha, the full shell. Don't worry about the half skeleton, and here's the skeleton. And that's the one I was showing you earlier. Okay, this guy here. The lucite skeleton ear mold, that's the center one. The full shell on the left is usually made of silicone. Profound loss, severe loss, and then what are these hearing aids? These thin tube hearing aids and receiver in canal hearing aids? Mild to moderate sensorineural loss. 90% of your clients are going to be wearing these guys. Either it's a thin tube or it's a receiver in canal. The style looks identical. They both end in little domes, okay? Same with this one here. They both have the same width of tubing, only in one there's a wire going through, the other has sound going through, but these are by far the most common styles of hearing aids today. The completely in canal is fairly common as well. You'll notice the blue writing on it. That means it's for the left ear. In all acoustics, red is for the right ear. Here's a red. That means the hearing aid goes in the right ear, and it's got the writing and the serial number. Blue means that the hearing aid goes in the left ear. It's like that in all audio with headphones, everything. Red is right, blue is left. Anyway, I digress. Let's go into the molds, or into the thing called vents. So now we will proceed in a southerly direction. Here is a summary of the 3 things we're going to talk about. The biggest one is venting. So these are the 3 non-electronic modifications. These are the 3 non-electronic, has nothing to do with the software, nothing to do with the programming. This has nothing to do with anything but shapes and sizes. Here goes. Venting affects the low frequencies. You can see it here on the graph. Filters are called dampers. So again, a filter might be seen as this little guy in the end of the hook. Here's a filter. See, if I can show it, it's hard to see. You'll see a little gray thing at the very end of the hearing aid. Tough to see. It's a little tiny gray thing jammed up there. That's a filter. Here's another example of a filter. That little red one. Here's an ear hook of a BTE, and that little red thing jammed in there. That's a filter. Now, filters are little screens. We'll talk about them next, but vents first, then filters, and last of all, horns. I shared screen too quickly. So horns affect the highs, filters affect the mids, vents affect the lows. So let's look at this a little bit better. Look at it a little more closely. Here's venting on the left. Here's filtering, although filters are almost never put in the tube of a hearing aid. As I showed you, filters are more in the ear hook. This is called the ear hook. The thing that hangs the hearing aid on the ear, that's the ear hook. And of course, the ear hook is attached, of course, to the number 13 tubing, as I will show you here. Okay, ear hook, tubing, mold. Okay, silicone, full shell, lucite skeleton, number 13 tubing, 2 millimeter diameter on the hook. Filters are usually in the hook of the hearing aid. Anyway, and horns, I'll show you last. So here we go, share screen again. So vents, and so look at the left. Here's the tubing. There's where the sound is coming through, and here's the vent. Okay, filters are never in the tubing anymore. This is a stupid picture. Okay, and over here, look at the horn. It's number 13 tubing again, 2 millimeters in diameter, but look what happened. It flared out to 3. It got wider. It's a horn. So, and as we said before, horns affect the highs, filters affect the mids, venting affects the lows. Now, so here you go, the lows, the mids, and the highs. So when you're looking at vents, oftentimes what comes, let's see, you've ordered an ear mold, they're going to cut a hole in it, that's the vent, and you will be given, along with the ear molds that come to your shop, you're going to see a weird little thing, little plastic thing with little buttons in it. And that's called a select vent. You can pick the size of hole that you want in the hearing aid. Okay? And you're doing that by looking at the guy's ear canal and finding out, see, here's the vent, and here's your select vent. You can choose one of these guys off of the tree, pick which apple you want. Don't be Adam or Eve, okay, because they ate the wrong one. Anyway, pick the right one and stick it inside the mold, the hole, and you can change the size of the vent. It's called SAV, select vent. Now, why do you have vents? So now I'll stop sharing and you got to look at me and I get to look at you. Why do you have a vent? It's to reduce the occlusion effect. Plug one ear, put one finger in an ear, and now start humming. Talk to me. Hey man, how are you doing? Blah, blah, blah. Go ahead. Start talking. Where do you hear your voice? You hear your voice in the ear that you plugged. Okay? That's what's going to happen with a hearing aid. As soon as you take a hearing aid and stick it in your ear, you're going to hear your voice loud because you're plugging up your ear. Occlusion effect. So, a bunch of things happen when you stick a hearing aid in your ear. You lose the high frequency resonance, so the hearing aid's got to give it back. You've got an occlusion effect. So you need to have a vent, because a vent reduces the occlusion effect. That's why you have them. And who gets fit with vents? People who have good hearing in the low frequencies, because they are the most bothered by the occlusion effect. If a guy's got poor hearing in the low frequencies, who cares if he's got the occlusion effect? It's actually a good thing. It helps him hear his own voice better, okay? But most people don't. Most people have trouble hearing treble. It's called the trouble with treble, presbycusis, Presbyterian, Church of the Elders, presbycusis, hearing of the elders, okay? Trouble hearing treble. Bass is okay. So guess what? When they plug up an ear with a hearing aid, they're getting the occlusion effect. So who needs a vent? Almost everybody. Because most people have good hearing in the lows and it drops off in the highs. Occlusion effect. Let's look at our notes now and see where we are. So I'll go from here and we'll go to the next one. And here's the effect of vents. So look at this graph. Look at the picture. And I'll tell you what vents are measured in. Vents are measured in millimeters. They're not measured in decibels. They're not measured in frequency. They're not measured in attitude. No, but they're measured in millimeters. What's the diameter? How big is the hole? So look at this graph with me and I'll show you what I mean. So here's a hearing aid. Here's the hearing aid I showed you with a silicone ear mold and no vent. Okay, this is meant for the profound hearing loss. Now, look at what the closed ear mold here. Closed ear mold. What is it doing to the lows? It ain't letting any of the lows out. Nada. Look at this. Follow my cursor. None of the lows are let out. If I make a 1 millimeter vent, a little bit of lows are out. If I make a 2 millimeter vent, look at this, more lows go out. And the bigger the vent, the more the lows go out, which reduces the occlusion effect. Now, when you took anatomy, remember we covered the occlusion effect? And what is it? The layperson says, my voice gets louder when my ear is plugged. Okay, that's the lay definition. Good. The professional definition. Low frequency, bone conducted sound. You see, you hear yourself through the air, but you also hear yourself through the bone. How do you hear other people? You hear other people through the air, only through the air. You ever listen to a recording of your voice? You're the only one that hates it. Everyone else thinks it sounds just like you. But you're the only one that says, no, that doesn't sound like me at all. How come? Because you are, for the first time, hearing yourself as others hear you. When you're listening to a recording, you are hearing yourself through air conduction only. When you listen to yourself talk, you're hearing yourself through air conduction and bone conduction, both. Okay? So you hear yourself louder and more deeper, richer, more of a low, you hear yourself more low-pitched, and you hear yourself louder. So now here comes the definition of the occlusion effect. The lay definition, my voice is louder when my ear is plugged. Professional definition, low frequency, that's number one. Number two, bone conducted sound, like through the bone. Okay, low frequency, bone conducted sound resonates the mass of the skull. So you got three things. Low frequency, bone conducted sound resonates the mass of the skull, which in turn vibrates the cartilaginous portion of your ear canal. Okay, so now you got four things. Low frequency, bone conducted sound resonates the mass of your skull, which in turn vibrates the cartilaginous portion of your ear canal. And 5, plugging your ear prevents that resonance from escaping. Plugging your ear prevents that resonance from escaping. Low frequency bone conducted sounds rattle the mass of the skull or resonate the mass of the skull, which in turn resonates the cartilaginous portion of your canal. Plugging your ear prevents that resonance from escaping. That is the occlusion effect. That's why you have vents, because vents allow the lows of your voice to escape. Do you want to know technically what vents do? Technically, a hole in the hearing aid, it increases the acoustic mass of air. Instead of having a little sugar cube of air trapped behind the ear mold and the eardrum, now you've increased the acoustic mass. And like Hansel and Gretel, the low frequencies are going to follow the crumbs out of the woods because lows resonate with mass. When you have a vent in the mold or in the hearing aid, you have increased the acoustic mass of air. And lows resonate with mass. And that's why lows will follow and get out of the vent. They will go through it because they're trying to find, they want to resonate with more mass. And the vent increases that because it allows the air to communicate. Okay? Such is the story about vents. So now let's go to our notes and read the actual notes that are below it. So the bigger the millimeters, the larger the millimeters, the more the lows escape. So when I was showing you hearing aids like these open fit hearing aids, these got 3 holes in them. So that's got like 4 millimeters worth of vents. That's a great big open fit hearing aid. That's meant for someone with excellent hearing in the lows, worse hearing in the highs. If the person's hearing isn't excellent in the lows, you can take off this dome and you can put on another dome with fewer holes, smaller holes, because maybe that person's got more of a flat loss and doesn't need a big vent. So these little domes are very, very exchangeable. And if you have a mold like this, you can adjust the size of the vent with Select a Vent. Okay, so either way, these vents are adjustable. I want to just tell you, though, there's a tension. Not paying attention. There is a tension between the size of the vent and feedback. Okay, because if you have too big of a vent, you may release the occlusion effect. Oh yeah, but your hearing aid's going to whistle, and it might whistle Dixie, and you might be a northerner, and you might not like the sound of Dixie. Okay, know what I'm saying? It's going to. Now, gotta watch them Yankees. Telling you. Anyway, so. And here I am talking from Canada. What the heck am I? Well, up in Canada, yeah, quite. Yeah, you know the Queen has been married. Okay, quite. Now, so what we need to know is that if the vent is too large, you're going to get excessive feedback because sound is going to leak. What is feedback? It's when you're talking in a mic. So I'm talking in a mic, and I'm going close up to the speaker. So the speaker is this bag up here hanging on the room. And I go too close to the speaker, and now the sound from the speaker is entering the mic. Not just the sound from my voice, but the sound from the speaker is coming in. And I'm getting a vicious cycle. And that's what happens when you're talking in a mic and you go too close to the speaker. Same thing happens in hearing aids. Sound comes out of the mold, bounces off the eardrum, leaks out of the vent, gets picked up by the mic of the hearing aid, amplified, down the tube, out the mold, hits the drum, bounces out, leaks out of the vent, and you've got that vicious cycle happening. Feedback. Always remember there's a bit of a tension there. So you have to kind of, as a clinician, you got to, but the good thing about today's digital hearing aids is they've got automatic feedback reduction too. And so that's why you don't have to worry as much as we used to have to worry about managing feedback. So anyway, now let's go over to the actual notes themselves so we can cover this. So we did that. Ear molds, types of materials, we covered that. We talked about that there's 3 general things, and we spent most of the time talking about vents. The bottom of page 1 really talks more about vents. I'm highlighting it so we can look at it. Put my glasses on so I can see it. Short, wide hole in ear mold done to reduce low frequency amplification, creates more acoustic mass, allows lows to leak out. Larger vents allow more lows to leak out. Venting reduces occlusion effect, especially for those with good low frequency hearing who have high frequency hearing loss. Select a vent for BTEs, ITEs, one large vent with series of progressively smaller plugs. Allows you to customize venting for client. Don't worry about parallel versus diagonal, couldn't care less. Pressure vent, put a star. Pressure vent is a very small vent. A pressure vent is 1 millimeter. A pressure vent is too small to do much to the sound. So if we stop sharing and I pull up, well, let me get my the PowerPoint slide here actually so we can see that, okay? Here's a picture of a pressure vent. Look at the 1 millimeter. See that 1 millimeter? Here's what would be a pressure vent. Tiny. It's just a 1 millimeter vent. It hardly does anything. It's just meant for physical comfort. It's just to allow air to communicate on both sides of the eardrum of the hearing aid, so that when you pull the hearing aid out, you don't suck out the eardrums and the 3 middle ear ossicles along with it, if you know what I mean. Okay? It's a pressure vent, not meant to do much to the sound at all. All right. Note on PowerPoint slides where vents are seen on BTEs and ITEs. Well, I've shown you that, so we're good to go there. Filters. Now we're talking filters. The second acoustic modification. And if you look at filters, filters are a little bit different. So here's venting effects too. We're talking about what they do. The bigger the diameter, the more the lows escape. This one's talking in terms of dB SPL. This one's talking in terms of relative gain dB. Either way, they're telling the same story. This slide, this slide, this slide, this slide, venting, venting, venting. Here's filters. Now here's a frequency response of a hearing aid. A typical, fictitious, once upon a time, behind the ear hearing aid. Okay? And it is a behind the ear, not an in the ear, behind the ear hearing aid. Some honker, it sits like so. Now, you've got 5 bumps. Count them. 1, 2, 3, 4, 5. These are peaks in the frequency response. Peaks in the frequency response. These are going to cause feedback. Okay? So filters, and you've learned this now earlier in the course. Filters, remember the word impedance? Remember we said the word impedance earlier on in our course? Impedance, stopping, impedance. The flip side of resonance, remember we described that? We said impedance is opposition due to mass, because mass doesn't like highs. Mass is a bouncer that says, sorry highs, you can't get through. I resonate with lows. And stiffness is the other bouncer that says, I don't want you coming through lows. I'm a stiff object. I resonate with high frequencies. Okay? Opposition due to mass, opposition due to stiffness. The third part was resistance. Remember that one? Like simple friction. Any object that transmits sound, any object that carries sound through it, has its own opposition due to mass, opposition due to stiffness, and resistance. Okay, back to filters. Filters are resistors. And filters look like this. They're tiny screens. See the screens? You ever have listen to the wind howling through the screen in a window? or the wind howling through the screen in your front door. And it's almost going to whistle, isn't it? The screen, the tighter the screen, the more resistance. Now, filters are called resistors because resistance in any object is equal for all frequencies evenly. In other words, resistance is not, I repeat, not frequency dependent. And so filters are measured not in diameter, not in millimeters like vents. Filters are measured in ohms. Now, you think of an electrical wire. Electricity has a current, and any wire that conducts electricity has ohms, resistance. Okay, ohms is called OHMS, resistance. What's the resistance of the electrical wire to the passage of current? Well, that's how filters are measured. How many ohms is it? Is it 600 ohms? Is it 1,000 ohms? Is it 2,000 ohms? What's the how tight is the filter together? What's the fineness of the filter? And remember, filters are always placed in the ear hook of the hearing aid. That little red thing. There's a tiny little screen. And if you had that little red thing under a microscope, it would look a lot like this guy here. It would look like a screen, okay? And the more tightly clustered the ohms, the wires are together, the greater the ohms. So what do filters do? They dampen the peaks wherever the peaks may be, all right? So in a BTE, the largest peak is usually around 1,000 hertz. Okay? So the greatest effect of the filter is going to be seen at 1,000 hertz. But if you're looking at the effect of filters overall, look at these peaks. None, no filter, so you got buku peaks. And then you've got 680 ohms and 1,500 ohms and 3,000. And the greater the ohms, the more the peaks are flattened out. And it doesn't matter at what frequency they are. It's just that in hearing aids, the biggest peaks are around the mids, and so that's where the greatest effect is. But other than that, essentially, filters tend to dampen or reduce the peaks wherever the peaks may be. Why would you use filters? Two reasons. You use filters, first of all, to increase the quality of sound. So you don't have those 5 stinking teeth jamming your ear canal. You're smoothing out the frequency response of the hearing aid. Second of all, high frequency peaks are the ones that cause feedback. You see, you remember in acoustics, lows are long waves, right? So lows bend around things. Elephants emitting low frequencies. They're yards in length. Low frequencies bend around things. Bats, remember we said bats emit high frequencies. The little tiny short waves, they don't bend, they bounce. So what frequencies are going to cause feedback? Highs, because they're going to bounce off the eardrum and leak out the vent. It's not the lows. Okay, high frequency peaks are going to cause feedback. So you want to get rid of those puppies, especially the ones I'm circling right here. You want those suckers gone. Okay, now that was especially a concern for analog hearing aids. Today, we have automatic feedback reduction. Get this, your hearing aids today, this is sick, they measure what the feedback frequency was. Oh, I think I'm getting feedback at 3,424 hertz. Oh, so then they're going to make a 3,424 hertz tone in opposite phase. And they're going to play it in your ear canal, which cancels out the feedback. It's weird. So your hearing aids are digital. They'll sample the sound that's doing the feedback, and they'll create a tone that's inverse in phase to cancel it out. Automatic feedback reduction. Anyway, if I don't shut up, we'll never get through. So we're almost done. Let's carry on here. We done filters. Now here's just some review here. Here's your BTE. This is just show and tell. We're just talking here. I'm going to make this a little bit larger so we can see it more better. Here's the mic of a BTE. Here's the head, the speaker, the receiver. right where I'm circling. This is called your ear hook. This is called your tubing. What's the number of the tubing? Number 13. What's its internal diameter? 2 millimeters. What type of mold would this be? A skeleton. Made out of what material? Lucite. Here's the vent. Here's the tubing. Here's the vent. Volume control, off, telephone, mic switch, battery on the bottom, okay? The guts of a BTE, but remember, these are more for severe hearing losses. The basic parts of a BTE, again, just showing you more in color. Once again, the tubing, the ear mold. This one isn't showing a vent very well, but the microphone is a little dot right where my arrow is, and the receiver is a little speaker right there. Okay, number 13, tubing. Location of filters. Look where the arrows are drawing. If you're going to be using filters in hearing aids, the arrows are usually showing you that the filter is in the ear hook. If they are used. Filters are not always used anymore. Vents still are huge. Filters, not so much. Number 13, tubing. It's always bent. You're going to snake this into the ear mold impression. You'll be learning how to do this in your labs. Okay, how to replace tubing in an ear mold. This is an open fit BTE. Notice the size is smaller, but the tubing is also no longer number 13 tubing. It's how wide in diameter? 0.8 millimeters. Occlusion effect is reduced. Huge. This dome here isn't showing many holes, but it should, okay? Because I showed you domes too. They've got buku holes, okay? Great, big, tons, and look at the holes in that puppy. Even in the corner of the screen when I'm not sharing. Okay, have a look at that. I mean, that's, so major vent action. Cosmetics of completely in canal hearing aids. Here's, I like to always do this. Here's a completely in canal hearing aid. CIC, completely in canal. You know what I call them? Comes in clogged. You talk about high maintenance. Do not ever fit little old ladies with these hearing aids. The devil's going to come knocking at your door for having done so. That lady's going to be back, and she's going to be back because you sold her a high-end CIC, and she hasn't got the manual dexterity and the vision to change the tiny little battery. She's going to have the hearing aids in the wrong ears, and all I'm going to say is, you asked for it. Don't do it. Anyway, different styles, different strokes for different folks is all I got to say. Hearing aids that's the art of being a good clinician. Now, this is a thin tube, 0.8 millimeters diameter. Sound is going through this tube. The mic is going to be where my arrow is, the speaker or the receiver where my arrow is, and that's going to send the sound through the tube. Now, that's an open fit BTE. Open fit BTE. Okay, open fitting because usually it's got lots of venting. When you're using a thin tube, though, you're blocking out the highs. So a hearing aid has to make up for that. Look at the output with a 9 millimeter thin tube versus the output with a regular number 13 tubing. Okay, so the hearing aid has to make up for that lost highs. Now here's the most popular one, receiver in canal. So here, it looks just like the open fit shown here. They almost look identical. The only difference is that instead of sound going through the tube, follow my cursor, you have a wire going through the tube. And here's the speaker, and there's your open dome. Once again, lots of venting happening. Occlusion effect is reduced. Okay, these usually cost more. RICs, RICs, cost more than thin tube, open fit thin tube. Okay, these are a poor man's RIC. RICs are, but here's another picture of a RIC. Okay, receiver in canal. Wire going through the tubing, and the speaker is here. Okay, normally, otherwise in a thin tube hearing aid, The speaker is still back up there. It's important to kind of keep a grip of the differences. We're almost done. You've bared with me for 55 minutes. I'm going to take the last 5, hot diggity dang. What happens when you flare out? That's the third modification, horns. If I speak into a piece of paper, and you've heard me do this before, so I'm going to grab a piece of paper. I'm going to roll up this piece of paper like a horn. I'm going to make it big. If I talk into the wide end, my voice is muffled. Okay? That's how presbycusis hears. They hear you're cutting off the horn. Okay? But if you reverse it, you've just turned that frown upside down. Now how loud are you hearing my S's and F's and TH's? My treble is being amplified by a horn. Okay? So now if we stop sharing screen, have a look at this. Horns increase highs for free. They're simple. You talk about simple. What do they do? Look at the right side. If I have a reverse horn, if my number 13 tubing gets skinnier, I lose highs. If my number 13 tubing stays the same, well, that's okay. But if I make my number 13 tubing flare out like a horn, I'm increasing high frequencies for cheap. Not even doing it electronically. And here's an example of a horn. This is an ugly old ear mold with a yellow sponge plug. Okay, nobody sells these things. I'm just showing it to you so you know. This is number 13 tubing, 2 millimeters in diameter. There you go, you can kind of see the hole. Look at the width of this. Okay, it just got wider. If I pinch these and show them to you together, look at what happened. With my finger, it's 2 millimeters, and over here, the end is 3 millimeters. I've just made it flare into a horn. Okay? We used to do this commonly. A guy would come in with his BTE hearing aid, and he's not getting enough treble amplification. And instead of talking him into a new hearing aid, are you nuts? I'd take this. It was really wild. I'd take the mold, take it off his hearing aid, get a pliers, yank out the tubing, get a Dremel drill, and bore a more of a horn-shaped hole. And then I would take new tubing that was a flared horn into the ear mold impression with glue. And then I'd hook it back up to the guy's hearing aid. And he'd be going, wow, that's a lot sharper. Yeah, I can sure hear you. Yeah, how much did that cost? I don't know, about $1.50. Okay, just by flaring with a horn. So anyway, it's just people don't rely on horns anymore either because hearing aids today are all digital, so we don't have to. But vents are still highly utilized, obviously. There's your BTE, location of filters, tubing, open fit, thin tube, receiver in canal, horns, okay? Well, look at this one. I hit this thing that goes bling, bling. That means, shut up, Ted. You're done. All right. PowerPoint is now done. You have suffered and weathered through the course called acoustics. We're all finished. Okay? We started out with good old acoustics, frequency, wavelength, then decibel, then complex sounds, then midterms, then psychoacoustics, upward spread of masking, all that crap, and then today we just took it home with hearing aids. You're going to learn a whole lot more about all of these little critters that I've been holding in my hands. Hopefully you get some good hands-on lab application of it, because talk is cheap. You have to actually do these things to kind of get it in your head. But basically that there would be the idea. What are you taking next semester, you three? What are you taking?
I'm taking 130 and 140.
Good. That's good. You're not taking them at the same. How about you, Renee? Same thing?
Same thing, 130.
Yeah, good.
Good.
Good. Yeah, that's smart. I see that some people take all four of them at the same time, like 110, 120, 130, 140. All I can say is may God have mercy on your soul. Oh my God. Oh, because you're learning about a hearing test and you don't even know what a decibel is. You know what I'm saying? It's kind of like, putting the cart before the horse. So I think it's smart when you take 110 and 120 first, and then 130, 140. So, okay, blessings to you over Christmas. I hope things go well. I hope you kick butt on your final. Is this final proctored or not proctored?
I do not believe so.
No, this one's not. This one's not proctored.
That's going to be like shooting fish in a barrel. You'll be no problem. Okay? Easy peasy Japanesey. Good stuff. It's been really nice having you, that you guys attend each time. I really enjoy it, that I'm not talking into an empty computer screen. So this is great. Anyway, I hope you guys have a good Christmas over there. Success on your final exam. I'm sure you will. And I'm not sure. I don't think I'm teaching you next semester. I don't teach 130 and 140. I'm teaching, I think, 110 and 120 again to the new batch of to the newbies that are coming in. Anyway, live long and prosper.
Thank
See
you,
you when
sir.
we look at you. Stay in touch. I'm sure I'll be in Missouri and down in San Antonio one day. I know I'll be seeing you all again. All right.
Thank you, sir.
All right.
Adios. Bye-bye.